Hello and welcome to the fifth and final part of Unit 11. In this part, we are going to look at sample calculations of the moment of inertia. The first we're going to look at is a rectangular distribution of point masses. The masses are given below. M1 and M3 are 0.1 kilograms, M2 and M4 are 0.2 kilograms, and we're told the lengths of the sides. We're going to do this calculation twice. The reason we're going to do it twice is we're going to do it for the rotation about this axis and for the rotation about this axis, showing that you get different values depending on how you're rotating. In both cases, the moment of inertia is given by the sum over the mass multiplied by the distance that mass is from the axis squared. So in this case, it would be m1 times r1 squared plus m2 times r2 squared plus m3 times r3 squared plus m4 times r4 squared. Let's consider the first axis, which is going to be this one. So if we think about axis 1, then mass 1 is 0.1 kilograms. And the distance that mass 1 is from the axis is 0.3 meters. Plus mass 2, which is 0.2 kilograms. And it is also 0.3 meters away from the axis. Plus mass 3, this one, which is 0.1 kilograms. Also 0.3 meters away. Plus mass 4, which is 0.2 kilograms, times 0.3 meters squared. And if you multiply and add, that gives you a moment of inertia of 0.054 kilogram meters squared about axis 1. If we now go to axis 2, then the moment of inertia about this axis will be 0.1 kilograms for mass 1 times the distance mass 1 is from our second axis, which is this distance, or half of 0.2. And that, if you look, will be the distance for all the masses in this case, just as we had similar for axis 1. And I wrote that as 0.2 again. Dreadfully sorry, it should be 0.1. And that works out to be a moment of inertia of 0.05 kilogram meters squared. So why is the moment of inertia about axis 1 bigger than the moment of inertia about axis 2? What it comes down to is that the masses are located further from the axis, and therefore they are harder to rotate, giving the larger moment of inertia for axis 1. Next, we're going to calculate the moment of inertia for a long uniform rod about one end. So this will be our axis of rotation. We know from the table that the moment of inertia for a rod about an end is given by the mass of the rod times the length of the rod squared, divide by 3. So that is what we're aiming for, the end result of this calculation. For this calculation, we need to integrate the r squared dm. dm is a little chunk of mass right there. And as we saw when we did center of mass calculations, we can rewrite the dm in terms of the density multiplied by a little piece dx, assuming that this is our axis x. Because it is a uniform rod, the density will be the total mass divided by the total length. So that makes our dm equal the total mass divided by the total length times dx. R will be the distance from the axis to where our dm is. So that would be here. In this case, R is going to be a distance x. This makes our integral x squared times m over L dx, integrated from 0 to L for the total length of the rod. The m over L moves out of the integral. The integral of x squared dx becomes x cubed over 3 evaluated from 0 to L. Plugging in the limits gives me m over L times L cubed over 3 minus 0 cubed over 3. Because it's a 0, this term does not contribute, and I can take the L cubed, cancel one of those with the L underneath, leaving me with L squared, resulting in the expected result of ml squared over 3. Next, we're going to look at calculating the moment of inertia of a hollow cylinder. To do this calculation, we need to work in cylindrical coordinates. I have pulled this figure from a textbook that I have outlining what the volume unit is in cylindrical coordinates, because I can't draw it as well as they can. I just can't do it. Okay. So here we have our volume integral, our volume element. This side is a rho d phi. This side is a dz. And this side is a change in radius. And notice, instead of using r for radius in this one, they are using the variable rho. That makes dv equaling rho d phi times dz times d rho, or typically written as rho d phi dz. Okay. Now, remember, for this figure, the radius was given as rho. Okay. When we do our calculation of moment of inertia, I'm going to change the radius variable back from rho to r because I need rho for density. Okay, so let's find the integral of, or let's find the moment of inertia of this hollow cylinder. I'm going to define an axis coming down straight through and let the origin be at the bottom. The inner radius I'm going to let be at capital R1, the outer radius at R2, and the height of the cylinder I'm going to let be L. I'm now going to define a little volume element inside here. So that dm will be rho, which is the density in this case, times r dr d phi dz. So as a reminder, rho is a density. Because we're going to assume a hollow, or not a hollow, a uniform cylinder, that density will be the mass divided by the volume. But we know what the volume of a cylinder is. That's going to be the mass divided by the area of the bottom. So pi times r2 squared minus r1 squared times the height, L. We're now in a position where we can calculate the moment of inertia, the integral of r squared dm. R is the distance from the axis to our little chunk of mass. So plugging in, that's the integral of r squared rho times r dr d phi dz. The density is constant, so I'm going to pull it out of the integrals, and I'm going to have 3 integrals. I'm going to have integral from r1 to r2 of r cubed dr. There's two r's here and one more there. The integral from 0 to 2 pi d phi, because I've got to go a complete circle around 2 pi radians. And an integral from 0 to L dz. So that is the density. The integral of r cubed dr is r to the fourth over 4, evaluated from r1 to r2. The integral of d phi is phi, evaluated from 0 to 2 pi. And the integral of dz is z, evaluated from 0 to L. So now I can plug in my limits of integration. That's r2 to the fourth minus r1 to the fourth, all divided by 4, times 2 pi minus 0 times L minus 0. Simplifying, this becomes the density times 2 pi L divided by 4 times r2 to the fourth minus r1 to the fourth. Now I can simplify this further, and so that is my next goal. Okay. So writing down the result from the last part, the moment of inertia was the density times 2 pi L divided by 4 times r2 squared minus r1, not squared, sorry, to the fourth. That was the last line of the previous slide. Rho times 2 pi L over 4 divided by the radius is to the fourth subtracted. Okay. Now I'm going to plug in the density. Density was mass divided by pi r2 squared minus r1 squared L. I still have my 2 pi L over 4, and I still have my r squared to the fourth minus ir1 to the fourth. Okay, pi's cancel. The L's cancel. The factor of 2 in the numerator cancels part of the factor of 2 in the denominator. So now I have m over 2 times r2 to the fourth minus r1 to the fourth over r2 squared minus r1 squared. And now I want to remind you of something. If I have x squared plus y squared multiplied by x squared minus y squared, this works out to equal x to the fourth minus x squared y squared plus x squared y squared minus y to the fourth. The cross terms cancel, and I'm left with x to the fourth minus y to the fourth, which is exactly what I have in the numerator, with x being r2 and y being r1. So I'm going to rewrite this as r2 squared minus r1 squared times r2 squared plus r1 squared, all over r2 squared minus r1 squared. These two cancel, and I am left with a moment of inertia, I equals m over 2, r2 squared plus r1 squared. Notice, in the case of a solid cylinder, if it's solid, then my inner radius equals 0. And the moment of inertia for the solid cylinder is m over 2 times the radius of that cylinder squared, which is consistent with what is given on the table of integrals provided in the last part. Finally, for our last example we're going to work in spherical coordinates and calculate the moment of inertia of a uniform solid sphere. Again, I've copied a figure because I can't draw it this well. I really can't. In spherical coordinates, the variables are r, so from the origin out to wherever you're located, that's r. I take that back. That's cylindrical. Out from the origin up to where your volume element is. So from here to here, you can see that's labeled r. We have a variable phi, which goes in the xy plane around. So the limits there are going to be 0 to 2 pi. And we have a variable theta, which goes from the vertical axis downward, and it will have limits of 0 to pi. Okay. If we look at the volume element, this side is a dr. This side, which you can find with geometry, works out to be r d theta. And then finally, this side, which is the hard one to get, but again, it is possible with some geometry, works out to be r sine theta d phi. Putting that all together, we have dv equals dr times r d theta times r sine theta d phi. That's r squared, there's two of them, dr sine theta d theta d phi. And now let's look at our uniform solid sphere. Define a coordinate system which goes through the center of the sphere. I'm going to put my little volume element in right here. And we know that the volume element is r squared dr sine theta d theta d phi. I can define the little chunk of mass dm as rho dv, where rho is the density. And we're going to assume again that it is constant. So rho will be the mass of the sphere divided by the volume of the sphere. The volume of a sphere is 4/3 pi times the radius of the sphere cubed. So let's let our sphere have a radius of capital R. Or we can write that a little bit more nicely as 3 times the mass divided by 4 pi r cubed. Okay, we're now in a position where we can think about doing this integral. The integral we usually write as r squared dm, but we have a small problem here. And the problem is that r is the distance from the origin up to our little mass piece, which isn't the r that is intended here. The r that is intended here is from the axis over to that mass piece. I'm going to let that be a. Okay, so this is going to be the integral of a squared dm. Just to distinguish between r, which is going to be something I integrate over, and what is meant by this formula. Again, what goes in here is the distance from axis to that little dm, from the axis over to dm. We have a triangle now. That triangle looks like this. We have r on the hypotenuse. We have a on this side. And this angle, if we look back, is by definition theta. You can see it right here. So this is theta. I can now rewrite a as a equals r sine theta. So I'm going to have r sine theta squared times my dm, which is r squared dr sine theta d theta d phi. Okay, grouping this all together, I have r squared times r squared, so that's r to the fourth. And I lost the density. Let's put the density back in, shall we? We'll put it right there. Okay, we're also going to assume the density is constant, move it out of the integral. So the moment of inertia will be the density times, again, r squared times r squared is r to the fourth dr. I have sine theta squared times sine theta. That's sine of theta cubed d theta d phi. I'm getting a little crunched for space on this slide, so I'm going to go to the next slide. Okay, so where we were, I was the integral of the density of r to the fourth dr sine of theta cubed d theta d phi. Okay, so this works out into three integrals. An integral from 0 to r of r to the fourth dr, an integral from 0 to pi of sine cubed theta d theta, and an integral from 0 to 2 pi d phi. This integral over r is easy to do. That becomes r to the fifth over 5 evaluated from 0 to r. The integral on the end, d phi, is also easy to do. Integral of d phi is just phi, evaluated from 0 to 2 pi. The integral of sine cubed theta d theta is not one that is typically done in quick and easy. We could pull out our calculus toolbox and calculate it, but that's not the goal here. The goal here is to do the integral. So for that, I went and I looked it up in an integral table. And it turns out the integral of sine cubed theta is 1/3 of the cosine of theta cubed minus the cosine of theta. And I need to evaluate that from 0 to pi. Okay, again, I looked at an integral table. Translation, I Googled it. There you go. I'll be honest. Okay, putting in the limits, we have r to the fifth over 5 minus 0 to the fifth over 5. We have 1/3 times the cosine cubed of pi minus the cosine of pi minus 1/3 times the cosine cubed of 0 plus, minus a minus, this becomes plus, the cosine of 0. And then multiplying all of this, we have 2 pi minus 0. Simplifying, this gives me the density, which I'm now going to plug in as what we had on the previous slide, which was 3 times the mass over 4 pi r squared cubed, r cubed. I have an r to the fifth over 5. Cosine of pi is -1. -1 cubed is -1, so that's -1/3. Again, cosine of pi is -1, so that's a +1. Cosine of 0 is 1. Cosine cubed, or 1 cubed is 1, so that's a -1/3. Cosine of 0 is 1, so I have an additional plus 1. And then I need to multiply by 2 pi. Okay, there's some canceling that can happen. The r cubed can cancel part of the r to the 5th, leaving me an r squared. I have a pi here and a pi there. Those cancel. I have a 2 here and a 2 here. So I am currently at 3 over 10 times the mass times the radius squared. And then if I look at what's in here, I have 2 minus 2/3. 2 minus 2/3 works out to be 6/3 minus 2/3, or 4/3. So I have a 4/3. The 3's cancel. This 4 cancels some of that. I have a 5 left on the bottom there and a 2, which works out to be 2/5 times the mass times the radius squared, which is the moment of inertia of a uniform solid sphere given on your equation sheet or your table of moment of inertias.